السلام عليكم ورحمة الله وبركاته. يعطيك العافية شباب وصبايا. Our video for today is about elastic properties of materials, which is from chapter 8 in our textbook. At the beginning, let us talk about two types of forces, which is external and internal forces. Now, due to the external forces, the shape or the size of my object or material can be changed. And this change, we call it deformation. In contrast, the internal forces is only resist this deformation. In general, in this chapter, we are going to talk about this deformation. Why and how? As you can see here, this is my object of length L and cross-sectional area A. So due to this applied force, the length of this object stretched into or by amount or with amount of delta L or X. Now, let me go deeply and talk about stress and strain, which they are two important quantities in our chapter. So stress can be defined as the quantity that is proportional to the external force causing the deformation, where stress is force divided by area in unit of Newton per meter squared, which is same as the pressure. Second quantity, which is the strain, and can be defined as the result of a stress. In other words, it's measure of the degree of the deformation. Now, the strain can be defined mathematically as delta L or change L length divided by the original length. And please pay attention to this, to the unit of the strain. As you can see here, delta L or the change in length in unit of meter and the original length in unit of meter. Therefore, there is no unit for the strain. In this slide, I will talk about the stress and strain diagram. So as you can see here, I have a region from the origin all the way to point A, and it's linearly. Then beyond point A all the way to point B, and point C, and finally point D. Okay, let me talk about each point in details. As you can see here, from point or from the origin up to point B, we have linear region where the stress is linearly proportional to the strain. Now, beyond point A, in other words, from point A to point B, the stress is no longer linearly proportional to the strain, where B here is called elastic limit. In this region, from A up to point B, if we applied a certain force on our object, and this object stretched due to this force with amount of delta L. Now, if the applied force is removed, the object then will return into its original dimension. That's why we call it, or we can call this as elastic. From point B all the way to point C, as you can see here, we call this point ultimate tension strength. In other words, from point B into point C, increasing of the magnitude of the force or the applied force, actually, the strain will increase rapidly. And even if the applied force removed, the object does not return into its original dimension, same as at point or at the region from A to B. That's why we call this point ultimate tension strength. Now, from point C all the way to point D, keep increasing in the applied force, we will see additional strain is produced and fracture occurs at point D. That's why we call this point fracture point. Okay, so from the previous diagram, we see the stress is in direct proportional to the strain. Therefore, the constant of this proportionality is depends on the material being deformed and the nature of the deformation. Therefore, we can define new quantity, which is Young modulus, where the Young modulus measures the resistance of the solid to change in its dimension or length. As you can see here, Young modulus in our textbook, either E or Y equals stress divided by strain, and we know the stress is force divided by area, where the strain is delta L divided by L. And pay attention to the unit of the Young modulus, which is Newton per meter squared, because delta L over L, or the strain, has no unit. Example number 1. A bar of dimension 1 centimeter by 1 centimeter by 20 centimeter, as shown below here, subjected to a 1000 Newton tension force and stretched by 0.01 centimeter. Now, be careful. Where is the force acted? As you can see here, the point of action is in this side, not at the bottom. Now, find the stress. We know the stress is force divided by area, and we know force is 1000 Newton, but the area here is the area of this surface or this side, not the bottom side. So 1 centimeter times 1 centimeter, but be careful. The unit of area should be in meter squared. Therefore, we have the force and we have the area. Second, calculate the strain. We know the strain is delta L, which is given here, 0.01 centimeter, divided by the original length, which is 1 centimeter. Number 3, find or calculate Young modulus. We know the stress and we know the strain, or I mean we calculated the stress and the strain from part 1 and part 2. So all what we have to do is just divide the stress by the strain, then Young modulus will be 2 times 10 to the power 10 Newton per meter square. Another example, an object of a cross-sectional area of 6 times 10 to the power minus 4 centimeter square and length of 50 centimeter, if the stress is 5 times 10 to the power 7 Newton per meter square. Okay, I'm not going to the question. I have some comments. First, the unit of area or the cross-sectional area, it should be in meter squared. So you have to convert from centimeter squared into meter squared, which is divided by 100 squared. And the length here, it should be in meter. So 50 centimeter divided by 100 to convert it into unit of meter. Now, calculate the compressional load. Here, the question is asking me to calculate the magnitude of force. Okay, what's given here is the stress, and we know the stress is force divided by area. So from here, the force is stress times area. Second, if Young modulus is 0.9 times 10 to the power 8, times 10 to the power 10 Newton per meter squared. What is the strain? Okay, let me hide it. What is the strain? We know the strain from the previous slides. Epsilon equals delta L divided by L. So L, or the original length, is given, but the change in length is unknown. But the question here says if Young modulus is. So we know Young modulus, or Y or E, equals stress divided by strain. So from here, strain, which is sigma divided by, or the amount of stress divided by Young modulus. Number 3, find the amount of the compression. In other words, find delta L. Okay, we know that. So we have two ways to calculate delta L. First, we know the strain, which is delta L divided by L. So the strain is already calculated from part 2 and original length is given. Or we can say a Young modulus, which is stress divided by strain, which is force divided by area, all of it divided by delta L over L initial. Another example, block of mass 300 kilograms attached from the end of a steel rod of radius of 1 millimeter and length of 10 meters. Assume Young modulus of steel is 5 times 10 to the power 12 Newton per meter square. 1. Calculate the stress. Okay, imagine the rod all the way along y-axis, and there is an object or a block of mass 300 kilogram attached from the end of this rod. Now, clearly, the force due to this block is the weight and all the way down. Now, stress equals force divided by area, and the force here is the weight of the block, which is 300 times 10, and the area here, be careful, we are talking about the cross-sectional area. Now, we are talking about a circle, which is pi r squared. So we know the mass and we know the radius, and you have to convert it from millimeter into meter. Second part, find the new length. New length, which is L2. And we can see L2 and delta L equals L2 minus L1. So L1 is given, but L2 and delta L is unknown. Both of them are unknown. So we have to calculate delta L. So how to think about this? We know delta L as the strain times initial length. Now, let us calculate the strain, since the Young modulus is given and we already calculated the stress. As we can see here, Young modulus, which is sigma, or stress divided by strain. Therefore, the strain is 0.5 times 10 to the minus 2. Okay, so we have the strain and we know the original length, so easily we can calculate delta L. Now, since we have delta L, we can go back to this original formula. Delta L is known now, and the initial length is known, so the new length is delta L plus L1, or the initial length, which is by the end 10.05 in meter. Another example, two rubber rods of same length. Okay, same length means L1 equals L2, and different radii, or the first radius is 2 times the second. So from here, R1 equals to R2. The first rod is stretched by 1 centimeter, so this is delta L1. And the second rod is stretched by 2 centimeters, So this is delta L2. If the first rod is subjected to 100 Newton, so this is F1. How large is the force needed to stretch the second rod, where Young modulus is given? Okay, how to think about this problem? I have two rods, but both of them have the same material. Therefore, Young modulus for the first rod is the same as Young modulus of the second rod. So we can say Y1 or E1 equals to Y2 or E2. And we know Young modulus is force divided by area divided by delta L over initial length. So doing the following, as you can see here now. Let's go to what's given from the question. So the initial force or the first force is given. And delta L for the first rod is given. Delta L for the second rod is given too. But L1 and L2, both of them are not given. But here, as you can see, same length means L initial for the first rod equals L initial for the second rod. And we know the area is by R squared. We are looking for the cross-sectional area. As you can see here, now by with by cancel out, we will end up with the second force equals 50 Newton. The last subject in this chapter, which is Hooke's law. Let me draw the following spring with initial length, L initial, and there is a applying force, as you can see here. Clearly, when we apply the force, as you can see here to the right, that means the spring will stretch with amount L2, or I'm sorry, with amount of delta L, as you can see here. Now, how to relate Hooke's law or spring constant to Young modulus? Let me do the following. As you can see here, Young modulus, which is sigma or stress divided by strain. Now, let me calculate or solve this formula to find F. As you can see here, the force equal area times Young modulus divided by L initial times delta L. So area times Young modulus divided by the initial length is the spring constant. So compare this to this, you can say the spring constant, which is K, is area times, or actually the cross-sectional area. Again, when I'm saying area, I mean cross-sectional area. Now, times Young modulus divided by the initial length. Now, what is the unit of this constant? So you can use either this formula and say K is the applying force divided by change in length. Therefore, K, or the unit of the spring constant, is Newton per meter, or you can check your result using this formula. What is the spring constant of a human femur of length 40 centimeter under compression of average cross-sectional area of 10 to the power minus 3 meters squared and compression of compression of 4 meter? Okay, the spring constant K, which is A times Young modulus divided by the original length, where, yeah, I forgot to add this one. Young modulus for the human femur, it's in your textbook, is 1.6 times 10 to the power 10. So from here, we can easily calculate the spring constant, which is 4 times 10 to the power 7 Newton per meter. What is the compressional force? In other words, the amount or the magnitude of the external force. We know from here F equals K times delta L. We already calculated K, and we know the change L length or the amount of compression is 4 millimeter, but be careful. 4 millimeter, you have to convert it into meter, which is 4 divided by 1,000. As you can see here, so clearly the force or the external force acting on the human femur in this question is 16 times 10 to the power 4 Newton. Thank you and see you in next